constant 6.6.
Yeah. So each photon has energy. Each photon has energy E is equal to hf, where h is a Planck's constant. Which is 6.63 times 10 power minus 34. And if you're wondering what's the unit of Planck's constant, look at this one. This is joule, and this is per second. Frequencies, hertz, right, per second. So what should be the unit of h?
Joules.
Yeah, joule second. So unit of Planck's constant is joule second. And that's the energy of one quantum of light. And then we saw Einstein's explanation for photoelectric effect, which is hf minus work function is equal to kinetic energy max. Work function, this book writes it as W naught, but some books also write it as phi. I think your formula sheet for the AP tests will say phi. So if you see hf minus phi is equal to kinetic energy maximum, understand that, right? So it is, the symbol is not the main thing, but the format of the equation will tell you what each symbol stands for. But h is always going to be h, f is going to be always the same. So it's only this symbol that is changed. Some books use this, some books use phi, and I've seen some other symbols also used for work function. This makes sense because W work, sort of, right? But phi is also a symbol that is used. So just keep that in mind. And you also saw that this can be written as hf minus hf naught is equal to kinetic energy maximum. What is f naught? To cause photoelectric emission, which is called the threshold frequency. So f naught is called the threshold frequency, and f is the incident frequency of the light. This is the incident frequency of the radiation. This is the threshold frequency of the radiation. Obviously, when this is bigger than this, then only you have emission of electrons. So you can write it also as hc over lambda minus hc over lambda naught in terms of wavelengths is equal to half mv max squared, and this is mass of electron. So you can write it that way. Lambda naught is called the threshold wavelength. So get those connections. Lambda naught is called the threshold wavelength. C stands for speed of light, 3 × 10⁸. C is the speed of light, 3 × 10⁸ meters per second. And mass of the electron, is mass of the electron is 9.11 times 10 power minus 31 kilograms. And lambda is the wavelength of the incident radiation. Lambda naught is the wavelength, which is the threshold wavelength. And then we saw how this equation can be plotted on a graph. How that equation, kinetic energy max, is equal to hf minus work function. How that can be plotted on a graph, y is equal to mx plus b. So the kinetic energy max frequency, and the graph is going to be a straight line. The graph is going to be a straight line, and this point here is the threshold frequency. That is a threshold frequency. And this y-intercept is your work function. So x variable is frequency. So the slope m is what? Slope is equal to h, which is a Planck's constant. Now, if you experiment with a different material, instead of using potassium, if you use cesium or something like that, instead of studying the work function, studying the photoelectric effect on one material, change the material, and then what is the shape of the graph that you're supposed to get? Yeah.
It's the same slope, but it'd be
Same slope but a different work function. So you can expect a graph like that. Same slope but a different work function. You can expect a different work function there. Slope should be the same because slope is a constant, 6.63 10 to the power minus 34. So work function can be affected by the type of material. Now all these investigations can work well only if you are able to find the kinetic energy maximum, right? And to find the kinetic energy maximum, how you will be able to find the kinetic energy maximum of the emitted electrons. I think I started with that one. We need to stop. Try stopping. When you try to stop something, then you know how much energy you spend. Like for example, if your car is moving with a certain kinetic energy of say 10,000 joules. If your car is moving at 10,000 joules of kinetic energy, and how much work should you do to stop it? Negative 10,000, right? You have to do negative 10,000 joules of work in order to stop it. That's exactly what we do. How do you measure the kinetic energy maximum of the emitted electrons? We try to stop those. We try to stop them. And how do you stop electrons emitted? So this is called a photocell. I think I started explaining it, right? That's a photocell. Now this is the one which is coated with a certain material, let's say potassium or cesium. You can change the material there. Light comes and hits the plate. And when light comes and hits the plate, electrons are ejected. And if you just complete the circuit without anything in the circuit, don't draw the circuit right now, I'll tell you when to draw it. Don't draw this. So when electrons are emitted from here, these electrons, they have a lot of energy. They go and hit that plate and they complete the circuit. Not only that, when electrons leave this place, this becomes positive polarity. So this is also positive because it's connected. And so the electrons will complete the circuit, but electrons will start running like this and come here and get re-emitted. So this thing goes on. Which way is the current? Current is the opposite direction. So if I put an ammeter here, the ammeter will register that current, and that current is called photoelectric current. It is generated purely by photocell. Something like a solar cell. Okay? Similar idea.
Do solar cells run out of electrons?
Solar cells also does the same thing. Solar cell basically promotes that chemical reaction, and then so sunlight kind of promotes that reaction, which actually causes the current.
But like, do you have to like replace components of it? Because like
Components?
of the solar cell,
What
because
kind?
like if the sunlight's promoting a reaction,
Yeah.
then eventually won't the reaction not be able to happen anymore?
No, it is a cyclic process. It's a cyclic process there. It's not a chemical that is exhausted. It is just triggering the release. It's almost the same as this. It's like a photocell. This is pretty much the same idea. When sunlight comes and hits a metal plate, it pushes those electrons away, and that triggers the current in the circuit and goes on. This current can go on. As long as light is there, this current can go on. These are the kind of cells that are actually used. It used to be used earlier. Nowadays, they have other methods of doing it. This is the kind of thing that they used in elevators and all that. They used to use those lights. there will be light source from here and a photocell on this side. A light source through the door and a photocell on the other side. So when the light goes and hits the photocell, it promotes the current, which is sensed by the circuit, indicating that it's clear, right? But somebody actually steps and blocks the light. As soon as the light is blocked, this current abruptly comes down, and that is a way that the circuitry senses that somebody is on the way. So if you stand right in the middle, the door won't close. Why is the door not closing now? Because you stand in the middle, is because you're obstructing that. So unless things are clear, it won't close. But it is not a foolproof thing, because if it's a small child crawling and going, this photocell won't sense it. You understand what I'm saying? If a child is crawling through the elevator door, like Home Alone, you know, have you seen the movie? So if the light source is at a certain height and the child is crawling inside, the door won't understand what's happening and then can't close on. That can be bad. So nowadays they have sensors placed in many areas. So even if you put a finger anywhere, it'll sense it. Anywhere, any obstruction, it'll sense it. Yeah, so photocells were initially used for the audio of a movie projector, photocells. Anyway, so this is a photoelectric current that's produced, and this ammeter will indicate a current. And why is this ammeter reading current? Because these electrons have so much kinetic energy that they are able to go and hit there and continue the circuit. Now, one way you can actually reduce this current is by trying to repel those electrons away, right? So that's why we have a negative potential difference applied. When you apply a negative potential difference like this, so we are trying to make this side negative and this side positive. So we are creating a potential difference here, a negative potential and a positive potential. So what happens now? When the electrons are kicked out from here, the potential difference is going to work against them. There's work being done on the electrons, negative work being done on the electrons, because the electrons are running against the current, right? Electrons are going that way, and that's a negative polarity. So what happens to the electrons? Not all electrons will reach. Some electrons will fail to reach. Which ones fail to reach? Why don't all the electrons stop reaching at the same time? Can you answer that question? Can you answer this particular question? So as you increase this voltage from 0 onwards, as you increase the voltage from, so okay, when you put 0, you're definitely getting a current here. When you put 0 volts, you're definitely having a current. When I put 1 volt, will the current reduce or become 0? Will this current reduce or not at all? When I put 1 volt here instead of 0, if I put 1 volt reverse voltage, will this current be affected? My question is that. Yes? So that means electrons are not reaching there? Is that what it means? Will some electrons still reach? Yes? So why don't all the electrons stop reaching? Yes?
They all have different energy.
There's the answer. They all have different, that's why we said kinetic energy max. Why do we say kinetic energy max? Because we're only talking about the highest kinetic energy electrons. There are lots of them here. Some have really high amount of energies, they go there no matter what. And there are some which are absolutely slow ones. And 1 volt is enough for them to stop and go back. Right? So if the kinetic energy is a lot, like this marker, if I give a lot of kinetic energy, it goes and hits there. Right? If the kinetic energy is not much, it turns back. So from here, electrons are fired at different kinetic energies. There are some with the highest kinetic energy, there are some with lower kinetic energies. So when you start applying voltages 0, 1, 2, 3, what happens is the slower ones will start stopping earlier, right? The slower ones will fail to reach there. That means what? The current is going to be lower. And you increase it to 2, 3, 4, the current will go lower, lower, lower. And finally, when you reach a certain voltage, which is called stopping voltage, when you reach a voltage which is called stopping voltage, the current becomes 0. So when V is equal to stopping voltage, I is equal to 0.
Wouldn't that mean that it's possible that some electrons would go in and just get caught in the middle?
Oh, but they're coming back, basically. They're entering back again. Because you're putting a potential difference plus minus, they're reaching back again.
Was there like any instance where like they just go and then stop in the middle?
Creating a cloud of electrons, yes, possible. But then in this case, not possible because you're creating a positive polarity here, negative here. The ones which are actually going out from here, they will stop and they have to come back because this positive polarity is going to bring them back in. And they'll be re-emitted again. They'll fail to reach the other side. That's what it means. Okay. Yeah. So when the voltage is exactly Vs, a certain voltage which is called stopping potential difference. So Vs is the stopping potential difference. When the voltage reaches that, the current literally becomes 0. That means what? Even the fastest electron has been stopped. How much work needs to be done to stop the fastest one? How much work needs to be done? Is the kinetic energy maximum? Now tell me how much work was done. Electrons charge is E and the potential difference applied is Vs. So how much work was done on the electron? Yes, so work done is equal to QV. So the work done by the stopping potential difference is EVS. Makes sense? The work done by the stopping potential difference is EVS. Vs is stopping voltage. Which means that is the kinetic energy max. Because that's the work done to stop them. Make sense? Do you get that idea? So we managed to stop the electrons from reaching the other side, which also gives you the value for the kinetic energy maximum. Because the amount of work you did negatively was exactly the same as what is needed to stop those fastest ones. So we understand that this is true. Now come back to this equation. Come back to the same equation. Instead of Ke max, I'm going to write it as EVS is equal to HF minus work function. Now if I divide the entire equation with E, the charge of an electron, I get Vs is equal to HF over E minus work function over E. Now can you redraw this diagram once again? Because we are going to have, all these are going to change. Now you're going to plot what is on the y-axis? Vs. What is x-axis is F? What's the slope?
H over E.
Slope is H over E. Redraw this again, okay? Don't change your previous one. Slope is H over E, and what's the intercept?
W not over E.
Now, this is something that you can practically do. That experiment is a very famous experiment to prove a lot of things. I'll tell you what. Can you finish it off first? So that's an important experiment. Applying the reverse voltage and trying to stop the electrons, that's an important one. And that graph tells you a lot of information.
It's still F naught. Or intersection.
Yeah, all that stays intact. That's F naught. This is the threshold frequency, that stays the same thing. So now let's focus on this graph. When the incident light has a frequency of F naught, how many volts are required to stop them? 0. When the incident frequency is simply F naught, which is the threshold frequency, you don't require any voltage to stop them because they already stopped. Make sense? Mm-hmm. They just barely release, so there's no need to stop them. But if the frequency is higher, the higher and higher the incident frequency, the more and more Vs required. So you may need 1 volt to stop here, you may need 2 volts, 3 volts, 4 volts, depends on how much is the, so if the incident frequency is higher and higher, you will need more and more voltage to stop it. Get it? And this is an experiment that can be done practically because you can choose the color of the light. You can choose the color of the light that is coming and hitting. So frequency is completely in your hands. Voltage. How many volts are actually supplied? How many volts are supplied? How many volts are actually supplied can be measured, right? So we know this, we know this. So this graph can be plotted properly by changing the frequencies. You can actually plot these graphs. And what do you get out of those graphs? Number 1, slope is h over e, which means can you get a value for Planck's constant?
Yes.
See? The value for Planck's constant, you can determine it here, right there. Because nothing else is required. It's all proved now. E is the charge of an electron. H, according to this equation, H is the Planck's constant. And the other thing is, the line is coming out a straight line, implying Einstein's explanation of this photoelectric effect is 100% right, because the graph is a straight line. There's no other factor involved. So that is a straight line, verifying that this equation is right. And it also helps you to determine the work function of any substance. Suppose you want to know the work function of iron. Put iron, do the experiment, find out how much it is. So the y-intercept tells you work function over E. So this will tell you how much is the work function, clearly. And the slope tells you how much is the Planck's constant. So this whole experiment actually gives you a lot of information about the multiple things that is discussed in quantum physics. Planck's constant's value, photoelectric equation verified, work function of different substances can be found out. Right? Any questions here? Now let's look at some problems. Be ready for the problem solving. Take your calculators out and be ready. Here comes the first one. I'll just read out the question so you can just start thinking about it. What is the energy of photons emitted by an 88.5 megahertz FM radio station? What is the energy of the photons emitted by an 88.5 megahertz FM radio station? Question is asking what is the energy? Energy of the photons. If you have an answer, let me know.
5.86 times 10 to the negative 26.
Yeah. 5.87, right? 5.87?
Yeah.
Did you take, so the E is equal to HF, 6.63 times 10 to the power of minus 34?
I did 6.626.
Oh, okay. Yeah, those things will differ. Is it making so much of a difference?
Well,
It is?
Yeah, it's 5 I got 5.864. Times
Oh,
10 to the
okay.
negative
So
27, which is
5.86. Sorry.
3,000.
Okay. So 5.87 10 power minus 26 is what you end up getting with this number. 88.5 megahertz, mega. And then you get the answer, 5.87 10 power minus 26 joules. Next question. Okay? Everyone's okay with that? Got it? 5.87 10 power minus 26.
Yeah.
Okay. Next question is this. A typical gamma ray emitted from a nucleus during radioactive decay. We'll talk about radioactive decay later on in the next chapters. A typical gamma ray emitted from a nucleus during radioactive decay may have an energy of 300 kilo electron volts. So the energy is 300 kilo electron volts. So what they're saying is the gamma ray emitted from a nucleus has energy of 300 kilo electron volts. What is its wavelength? Go ahead and find out the wavelength. What is the wavelength? Kilo. What's 1 electron volt?
1.6 times 10 negative.
Good. 1.6 times 10 power negative 19. Put all these things and you get the answer. How much is it? Yeah. So you get 4.14 times 10 to the power of negative 12 meters. It's always a good way, it's always good practice to express in nanometers, because normally wavelengths, visible light wavelengths and everything is kind of compared in nanometers, so just like that. So 4.14 times 10 power minus 3 nanometers. That's how small it is. So the wavelength is 4.14, 10 power minus 3 nanometers. And the next part of the question is asking you this. Would we expect significant diffraction of this type of light when it passes through an everyday opening like a door? Can you expect a significant amount of diffraction if this light is passing through an everyday opening like a door? Now we're talking about diffraction. Chapter 24. Angle of diffraction. The sign of the angle of diffraction is what? Lambda over? Right? You know that, right? So how much angle of diffraction takes place depends on these. Lambda is this. What is A? The door width, almost a meter.
What is the question?
The question is, would you see an appreciable diffraction if this light passes through an everyday opening like a door? So definitely no, because lambda is so many nanometers and the door is 1 meter, and so when you divide this, sine theta is going to be so negligible, and so theta will be very, very small, almost zero, right? And so you cannot see any diffraction. You won't be able to see any diffraction. That's the answer for that. So why you're not able to see diffraction, you have to quote this formula down, because that's the diffraction formula. Single slit diffraction, that's the formula. This theta is the angle at which the first minima appears. Okay? Please go through all those things for the test. Next one. The human eye can respond to as little as 10 power negative 18 joules. The human eye can respond to as little as 10 power negative 18 joules. That means if that much energy enters your eye will see a flash. You get it? That's what it means. So again, I read. The human eye can respond to as little as 10 power negative 18 joules of light energy. For a wavelength at the peak of visual sensitivity, 500 nanometers. For a wavelength at the peak of visual sensitivity. What is that, visual sensitivity? Which color is that? Mm-mm.
Blue.
Which color is the most green? Green yellow. Green yellow. You know the vest that they wear? Traffic. Tennis ball. That color. That color is the most easily seen out of all colors. That one. Okay. So that color is 500 nanometers. That's what's saying. At the peak of visual sensitivity. So if you put violet light, it won't be so easily seen by your eyes, but that color will be seen. If I take this marker and this marker and this marker and this marker to a distance, you will definitely see this. Because this is, okay, from here you're able to see all of them, but showing this one, you'll definitely notice that because that is kind of bright. Well, it's not actually bright, but your eye is able to sense that better. Violet, terrible. Extreme end of red, bad again. So our visual sensitivity kind of goes like this. Violet, almost nothing. And then as it goes to blue, it starts better, better, better. And then when it goes to green, yellow, that area. And then after that, it starts declining. And then as you go to the extreme end of red, it goes off. So visual sensitivity is like that for all of us. All of us are, that's why the fire truck was initially red. They changed it all to the green thing. Now also there are some fire trucks that are red, right?
I've only seen red.
But they're changing. You're not seen red?
I've only seen red. I've never seen.
I've never seen
I've never
They're
seen
starting
red.
to
They're starting to switch, yes.
They're like the green.
Yeah, the red is the old one, but the red is not visible from a distance. That's why they're making the green. The red one was chosen initially because it's like more of a warning thing, but the green is more. I think it's the same thing as traffic lights. Which traffic light is more visible, the green or the red? From a distance.
They have the yellow outlines. It's in the traffic signals.
Oh yeah. That's just to show that there is something there. Yes. Which one? Green. Yes. Green is more easily seen from a great distance. Red is only when you go close.
Because we've already all associated.
So they said at the peak of visual sensitivity, which is 550 nanometers, that wavelength. I read it again. The human eye can respond to as little as 10 power negative 18 joules of light energy. For a wavelength at the peak of the visual sensitivity, 550 nanometers, how many photons lead to an observable flash? If you're able to see a flash of light, how many photons are required for that? That's the question. So number of photons. Go ahead, do the calculations now. Yeah.
What should we use as C?
Speed of light 3 10 power 8. So that's your lambda. So first thing you have to do is find the energy of the photon, which is hc over lambda. Do that, and once you have this energy, and you have this energy is the total required, you can figure that out. First find this, and that's the total energy required for sensing something. And this is the energy of each photon. What do you get? How many photons is the question? So once you find this energy, how many of this is required for that? That's the question. This is the energy of each photon.
7.
How much?
2.77.
2.7, which means what? 3. You can't have a 0.7 photons, so you have to have it 3. So at least 3 photons are required to enter your eye so that your eye can actually detect that flash. Make sense? What if you got the answer as 2.1? Still say 3. You don't round down. Because 2.1, if the answer comes out 2.1, 2 is not going to make you sense it. So you need to complete it as 3. So 3 photons are required. All right. Next one.
Like after you find the energy, do you know how many photons?
This is the number of, this is the energy for each photon. This is the total energy. So divide this with this.
Kyle asked a really important question that I wanted to do. Can you split a photon like into smaller parts?
That means there are smaller photons then.
Are there like smaller like is it
Photon is a bundle of energy.
so the
Photon is a bundle of energy. So you can have a smaller bundle of energy.
it would be the photon now?
It will be a photon, yeah. But if there's a blue photon going and hitting somewhere and losing some of its energy, then you can have a photon of a smaller photon going out.
Oh, so the photon would just get like really smaller because it's really small bundles.
I mean, depends on the wavelength, yes. Yeah. As it loses its...
There's nothing like small that should make a flash of light.
no, it all depends on the wavelength. Photons, energy depends on the frequency or the wavelength. Yeah. So you can have a photon, a big photon, small photons.
So there's like the most basic, something that you know of.
What, energy?
Yeah.
Now, photon is a bundle of energy. That's it. Nothing more than that. It's just a packet of energy.
Yeah, but doesn't that make it like one of the most basic things that we know? Because like, we don't.
You're talking about particle or energy?
Like particle.
Yeah, like the
Particle.
Like as far as like a particle would go.
Yeah, so particles, there are so many particles in particle physics. The particles that we will be talking more about will be like, when you go to radioactivity and all that, you'll be talking about, beta particles, small ones like protons, neutrons. We go to that extent. But there are so many more particles which are theoretically, some of them are quarks and bosons, fermions and all that. There are different particles which are theoretical. But there's no end to it. Particles are plenty. There is a branch of physics called particle physics. So in that you will be learning about so many different kind of particles, the smaller ones. Yes, you do go through beta particles, positrons, and beta particles and all that stuff. But that's particles. Now here we're talking about energy, right? Put it away. The next one. What is the longest wavelength of light that will emit electrons from a metal whose work function is 3.10 electron volts? What's the longest wavelength of light that will emit electrons from a metal whose work function is 3.10 electron volts? So basically the longest wavelength is what they want. What is that wavelength called? The longest wavelength which can emit electrons? That's a threshold one. Longest wavelength that can emit electrons is called the threshold wavelength. Because beyond that you cannot emit electrons with that. So you want threshold wavelength, and that's a work function. And you know work function is equal to hc over lambda naught, and then you start working from there. So 3.1 times 10 to the power of 3.10 times 1 electron volt, 1.6 10 power minus 19 is equal to 6.63 times 10 to the power of negative 34 times 3 10 power 8 divided by lambda naught. So that will tell you the lambda naught. So on that metal of this much work function, what is the largest wavelength that can actually cause photoelectric emission? Much?
1.5 times 10 to the 30. No, wait.
I got 4 times 10 to the negative 7.
Yes. It will be 401 nanometers. Yeah, 4.01 10 power minus 7. Yeah, so it will be 401 nanometers. Can you tell me what color it is? 401 nanometers.
One of them.
I have no idea what
Violet.
nanometers are.
I think I've told you this. Visible light goes from 400 nanometers to 750 nanometers roughly.
Oh, 4 to 750. That's
Yeah. So this is violet. So anything more than violet, anything more than this color, it's not going to emit electrons. Suppose it's ultraviolet, yes, it will emit electrons. You get it?
Are they? This may be a dumb question, but are they all split up evenly in between the different colors? Like, is does red have a little bit more of the?
Oh, it's different, yeah. I mean, the shades of red are all different, yeah.
Okay, I didn't know if I
I
could
mean, the
divide it.
proportions are all dependent. It's totally different. Because the wavelengths are not like discrete. I mean, they're continuous. Wavelengths are continuous.
Pardon this interruption. This is Dr. Zoller with just a couple of announcements and my usual send-off. First of all, good luck to all of you representing Trinity teams at tournaments and competitions this weekend. Go Rocks!
We're not finished with
A reminder that 5 houses have meetings on Monday: Aquinas, Beckett, Dante, Flannan, and Gonzaga. If you are in those houses, you have a casual dress day. You can wear your house shirts if you want. And the other 5 houses will have their house meeting day on Tuesday. Please remember who you are this weekend. Do the right things. We need you to be men of faith and character on and off campus, when you're online and in our community, during and after the school day, even when no one but God is looking, because that's the true test of your character. Enjoy the weekend. Find some time to rest and relax, get some extra sleep, and spend some time with God in prayer on Sunday, hopefully in church. Monday will be a white day, so make sure you take home all the books you need for homework. Have a great weekend.
All right. So, what is light?
Photons?
That question is still not answered.
What?
When photoelectric experiment was discovered, Einstein said, okay, this is how it works. Photoelectric experiment is explained properly, and now you know in and out of photoelectric effect. But the question of what is light is still a mystery, because Huygens theory could explain reflection, refraction, diffraction, interference, polarization, and everything except photoelectric effect. Einstein's quantum theory explains only photoelectric effect and none of the others. So what is then light? Is it a wave or a particle? And that is where this guy, de Broglie, or de Broglie as it is pronounced, he came up with a wave-particle duality theorem. Wave particle duality concept. Now, according to De Broglie, now the equation that he came up with is in connection with the relativistic equations and all that. So I'm just stating the equation that he came up with. He said that any particle or any matter that has a momentum has a corresponding wavelength. So he came up with this equation, which means lambda is equal to h over momentum. Now, if we carefully look at this equation, the left-hand side of the equation is something to do with waves. The right-hand side of the equation is something to do with particles. You see it? So this is the equation that connects wave-particle duality. So according to him, anything that's moving, if I throw this marker at you, that marker has momentum. That means it has a corresponding wavelength. So if I take a stone and throw the stone at you, the stone has a momentum, right? Because stone is massive, it will have a momentum. That means the wavelength will be small. Small wavelength means what? Higher energy. Can that kill cells upon impact?
Yes.
Definitely, it will kill a bunch of cells. When a stone lands on you, it can even kill you.
Oh.
Right. So it can damage a lot of cells compared to a single X-ray photon. Suppose you are talking about a single X-ray photon. An X-ray photon is probably going to kill 1 or 2 cells. But a stone can do more damages than that because the stone has more momentum. And therefore, a smaller wavelength. So if something is not moving at all, suppose something is not moving at all, at rest, what's its momentum? Zero momentum means what is wavelength? Infinite.
Oh.